In this problem, you are given the IR spectra, the mass spec, together with the molecular formula, so you don't have to calculate the molecular formula. You are given the carbon-13 data, the proton decoupled spectrum, together with the DEPT. This is the DEPT 135, because you can see that you have your CH2 as a negative peak. And then you are given the proton NMR spectrum. The first thing normally that you do is you get your molecular formula. But because you have the molecular formula, then you go to the second step in there. And the second step is to go ahead and calculate the DBE, which is the degrees of unsaturation in there. Since we have an oxygen in the molecular formula, if we have a DBE different than 0, then there's a possibility we have a carbonyl. And you can see over here the 1723, which is the carbonyl region in there. So go ahead and get the DBE. And the DB is equal to the number of carbons times 2 plus 2 minus the number of hydrogens, which is 10 in this case, divided by 2. And that is going to be equal to 5. So 5 means that you have a benzene, and the benzene is a DBE of 4. So you still have 1. Since you have an oxygen in your formula, then you will have a carbonyl. Let's go ahead and check for the benzene first before we move on. So if we have a benzene, see the benzene region between 7 and 8. This is the benzene region. So over here, this means that you have a benzene. Now, since you have a lot of peaks between 7 and 8 and not doublet of doublet, then this means that this benzene is going to be a mono substituted benzene. It is not a para-substituted benzene, because if it was, then we will see a doublet of doublets between 7 and 8. Now, this is the first thing that you do. Get your DBE, and then immediately after your DBE, I want you to go directly to your proton NMR spectra and to start analyzing your proton NMR spectra in there. Now, I know that the region between 9 and 10 is specifically for aldehyde. So this means over here that I have a carbonyl and a hydrogen. So that is for the aldehyde region. And the aldehyde has 1 hydrogen. Don't forget over here that you see the integration values in there, but you don't have the values, so you would need to calculate the integration values. With a ruler, you can use the screen. It's fine. Put your ruler on the screen. We know that you can make it easier though on you, because you can do an estimation, because you know for sure that this is going to be 1 hydrogen in there, and this over here is 5 times as big, and I know that it's a mono-substituted, then this is going to correspond to 5 hydrogens if this is a 1 hydrogen. And there, this has the same length. This integration here has the same length as this integration here. So probably this one is going to be 1 hydrogen. And I know that the first peak always is going to be a CH3. And this one looks like 3 times the distance of this integration. So this is going to be 3 hydrogens. Okay, you can do it this way. Another way is go ahead and get a ruler and go ahead and measure the distance between those 2 lines in there for each of the integrated value. So let's go ahead and do that. So the distance from here to here, it doesn't matter the units. I am using a centimeter. So this one's going to be 0.5. This one over here is going to be 2.4, and I've measured those off the screen. So, and this one is going to be 0.5. It's okay. You can put your ruler on the screen and measure. And this one is going to be 1.5. So go ahead and add these values up. 0.5 plus 2.4 plus 0.5 plus 1.5 in there. And that is going to be a 4.9. Okay, after you do this, take the 4.9 in there and divided by the number of hydrogens, because your molecular formula here is very important, and you cannot do the integration without knowing the number of hydrogens that you have. So this is going to be 10 hydrogens. Then this is going to be 0.49. Then you're going to go and take that number and divide it over each of these integrated values in there. So we're going to do 0.5 divided by 0.49, and that is going to be approximately 1. So our assumption here is right. Then you're going to take 2.4, you divide it by 0.49, and that is going to be around 5. And this one is going to be 0 divided by 0.49, and this one is going to be 1. And then you can take 1.5 and divide it by 0.49, and that is going to be around 3 hydrogens. So this way you can get the number of hydrogens that correspond to every single peak. So after you get your integration for every peak, then we know that the peak between 3 and 4, this is going to correspond to a CH. This is going to correspond to a CH3. And that CH3 is a doublet. So you can see the magnification of that. And this is a doublet. So for a CH3 to be a doublet, it needs to be connected to a CH. So let's go ahead and start putting our structure in there. So we have our CH3. And that CH3 is going to be connected to the CH. And this is why this hydrogen over here is going to be a doublet, not the carbon, it's the hydrogen though. So the hydrogen is going to be a doublet in there. That is going to check the multiplicity of the CH. And the CH is going to be a quartet. So this makes sense that because it's connected to the CH3, it's a quartet. This means that whatever group the CH is connected to over here should not have any hydrogens. Now my molecular formula is C9H10O. So far I have used 2 carbons, and I know that I have a benzene, and the benzene has 6 carbons in there. So I'm left with 1 carbon, which is the aldehyde. I know that the aldehyde goes always at the end. Now, because it's a monosubstituted benzene and it should be 5 hydrogens, I cannot put the aldehyde over here. Of course, I cannot put the aldehyde over here because I need the CH3. Since this one is a CH, then definitely the aldehyde is going to be connected to it. So that is going to be our structure in there. The CH is going to be a quartet. The CH3 is going to be a doublet. The aldehyde is always a singlet. This is always a singlet. It's not going to be split by any neighboring hydrogens. And then the hydrogens of the benzene, they appear as a lot of peaks between 7 and 8. So this way I have interpreted every single peak in there. So I'm done with the proton NMR. Notice from the proton NMR, I got my structure in there. We need to verify those 2 functional groups. So I need an aldehyde and I need a benzene. And you go straight to your IR. You could have started with the IR at the beginning, but it was very obvious in the proton NMR that we had an aldehyde. So that is going to be the carbonyl of the aldehyde. And every time we have an aldehyde, you would need to look at your IR table in there. And there are 2 peaks at 2720 and 2820, and these are the CH stretches of the aldehyde. So you would need to check those out in there. So here you go. So I do have those 2 peaks in here. These are the CH stretch of the aldehyde. These are the sp2CH stretch of the aldehyde. You can go ahead and write the wave number in there. Now, my structure is my benzene, my CH, and my carbonyl. And that's not a carbonyl, actually. It's a CH3. And the carbonyl is connected to the CH over here. Okay, so I do have an sp3ch stretch, and these are my sp3ch stretches in there. Okay, and then for the benzene, for the aromatic, always in the region between 1500 to 1560. So this region in here between 1500 to 1560, you should always see those two peaks if you have a benzene. And those two peaks are indication that you have the carbon double bond carbon stretch of the benzene together with the 1600 peak. Sometimes the 1600 peak does not show for the benzene. So we cannot rely on that because it's also common for alkenes as well. But for benzene, you have these two peaks for sure, and they always are going to be there in case you have a benzene. So all of these three peaks are going to be the carbon double bond carbon stretch of the benzene. This is it. So you don't need to interpret any other peak in the fingerprint region. Now, coming to the carbon 13, before you go ahead and you analyze the mass spec and the fragment of the mass spec in there. Now, for the carbon 13, I know that every different carbon has a signal. You guys, always the peak at 80, I want you to ignore because this is a solvent. It appears as multiple peaks every single time. Just go ahead and ignore. Now, I know that the region of the benzene is all of that. So this is for the benzene. Okay, and don't bother to count in here. We already deduced that it is a monosubstituted benzene, and especially because some of the peaks here, they are fused with each other, so don't bother to count this region. But you can easily see that you have a peak in here, a peak in here. So every peak is going to be a carbon. So I have a peak for my CH3 over here. And then that CH3 is connected to a CH. Now we know that the CH is more de-shielded than the CH3. So the CH is going to appear further than the CH3. And also, since the CH is connected to both benzene and carbonyl, and both of those cause de-shielding, this is why the CH3 is over here. So that is I'm sorry, this is why the CH is over here. So you have your CH over here. And then last over here, you do have your carbonyl. Because we said that the carbonyl absorbs at 200 parts per million. It has between 160 to 200 parts per million to show, and that's it. Now, when you run the distortionless enhancement proton transfer, which is the DEPT, this is 135. Some of the peaks are going to show as positive peaks. Some of them will show as negative peaks, and some of the peaks will disappear. So over here, I do have my positive two peaks in there. Then this is an indication definitely that I have a CH3 and I have a CH. Since I don't have any negative peak, then this means that I do not have a CH2 in there, which is consistent with my structure. These are for the benzene, but notice like one peak over here disappeared from the DEPT 135. And the reason why it's disappeared because DEPT 135 does not detect carbons with no hydrogens. So since this carbon had no hydrogen, and we are talking precisely about this carbon over here, it has no hydrogen. So this carbon did not show. So this carbon is over here. And this carbon is going to be nulled. It's not going to show in the DEPT 135. Now, because the aldehyde had a hydrogen, it showed. If it was a ketone, it's not going to show. It's going to disappear. So pretty much you got your structure over here. Now, the last thing that you need to do is figure out your fragments in there. So we have the 105. Normally, the fragment that you want to figure out is the base peak. This is the fragment that you want to figure out, and I'll be very clear in the question in there which fragment that you would need to find from your structure. So this is the base peak, which is the 105. I know that the molecular weight of my structure is 134. So this is going to be my molecular weight. And in case you didn't have the molecular formula, you would need to use this number over here, this molecular weight, in order to figure out your molecular formula based on the number of hydrogens that you calculated over here. Okay, so I need to find out the fragment, which is 105. I know that the molecular weight for this one is going to be 134. So this means that I am losing 29 in order to get to the molecular weight of 105. Now, I know 29 is an ethyl group, but I don't have an ethyl group in here. But I have something which also gives me a molecular weight of 29, which is the aldehyde. So if I lose the aldehyde in there, and the aldehyde is a carbon, oxygen, and the hydrogen. The carbon is 12, oxygen is 16, and the hydrogen is 1. Add those up, and this is going to be 29. So all what you need to do is just to fragment this molecule in here. This is the alpha cleavage, okay? This is your alpha carbon, and that is going to be the alpha cleavage. So fragment this molecule in here, and you're going to end up getting your cation plus your radical. So the cation is going to be the CH and the CH3, and this one needs to add up to M over Z equal to 105. This is going to be your base peak, plus the other fragment is going to turn into a radical, and this one, it's okay, you can skip that, you don't need to show it. This is not going to be analyzed by the mass spec. We can also find the second fragment over there. And the second fragment is 77. So all what you need to do is just subtract what are you going to lose from the 134 to get 77. And that is going to be a 57. So you take 134, you subtract from it 77, and that will be a 57. So 57 is this whole thing over here. This whole thing is M over Z 57. So if you lose that, you're going to end up having your cation benzene in this case. So go ahead and fragment this bond. And what you're going to end up having is your benzene as a cation. And this has M over Z equal to 77 plus your fragment, your other fragment in there as a radical. Again, you don't have to write it, but I'm just going to go ahead and write it down. So this is going to be my carbonyl, it's going to be my hydrogen, and the radical in there. So these are the two fragments that you are going to get. You are going to get the 77 M over Z, and you are going to get the M over Z 105. There are additional problems in the class notes, so please go over those. They do have a detailed solution, and every time follow the steps. So if you have the molecular formula, go ahead and get the DBE, and then start analyzing. Leave the carbon-13 and the mass spec till the end, but do the DBE, start analyzing your proton NMR, and then after this, go ahead and check your IR spectra and see what type of functional groups you have. If you have numbers above these peaks, this means that these are hydrogens. So here 6 hydrogens means that you have 2 CH3s in there, because the maximum number of hydrogens a carbon can have is 3 hydrogens in there if it's making a bond. So this means that this is a 2 CH3s. Normally, I either give you the integration and you get the number of hydrogens, or I give you the number of hydrogens directly, and that will show above every peak.